Vapor generators did not merely malfunction, they disintegrated with the ferocity of concealed munitions, transforming serene engine rooms into landscapes of debris. Within the nascent manufactories and vessels of the 1800s, laborers toiled mere paces from iron reservoirs, containing far greater energy than they could comprehend. Tension accumulated in quietude, the metal enfeebled without prior indication, and a solitary lapse in judgment could demolish a whole structure. Witnesses recounted walls being hoisted, floors quivering, and a detonation so abrupt the mind could not process it. What, then, caused these engines to fail with such ruinous finality? If narratives of this nature resonate with you, pray consider subscribing to our program to assist in safeguarding the obscured annals of our world's builders. Let us now examine the latent mechanics within vapor itself, and the men who discovered its perils through bitter experience. Steam capability arrived like a solemn assurance. It converted modest ateliers into industrial plants, and sluggish barges into the heart of mercantilism. Yet behind the self-assurance of the Victorian era lay a mechanism that almost nobody entirely relied upon. The primitive steam boiler appeared uncomplicated, merely a metallic casing containing water with a furnace beneath. To the stokers who tended them, they seemed substantial, everlasting, and sufficiently weighty to trust. Nevertheless, the reality was that these units were perpetually awaiting a moment of frailty. The boiler was a container crafted to withstand pressure, though that tension fluctuated incessantly. As requirement escalated, the firemen stoked the hearth more fiercely, and the liquid moved toward a vaporization point that was presumed to be foreseeable. Hypothetically, indicators and regulators maintained equilibrium. In actuality, the initial decades of steamcraft were a protracted trial. None knew precisely what robustness a boiler retained after years of use. They merely hoped the metallurgy preserved its integrity. Factories were reliant upon these apparatuses. Steam-propelled timber mills and weaving sheds, printing machineries and foundries. The clamor of rods and the discharge of valves became routine. Men passed by boilers without a second thought, despite each holding power capable of leveling a workshop. Laborers trusted what was familiar to them, and most had matured amongst furnaces and smithies. But steam was unique. It was imperceptible until discharge, and the tension within a shell behaved in ways even adept hands could miscalculate. The internal stresses were astronomical. Pressure does not mount like thermal heat. Gradual and constant, it can surge in moments. With the specific fusion of combustion and liquid levels, an obstructed regulator or an abrupt call for more energy could strain a boiler beyond its endurance before detection. The boundary between secure function and disaster was narrower than the industry cared to acknowledge. Early artisans presumed thicker plating ensured safety. The difficulty was that the iron itself was erratic. Puddled iron varied from one works to another. Some sheets were riddled with flaws that only manifested during a catastrophic failure. Riveted joints created points of stress. Junctions dilated and contracted with every thermal cycle. A boiler deteriorated from the interior outwards, its most perilous defects concealed where none could inspect them. This fostered a deceptive sense of confidence. If an enclosure appeared sound on its exterior, many conjectured it was sound within. Mishaps commenced early and never truly abated. The 1830s and 1840s were replete with accounts of steamboats shattering whilst mid-passage, mills collapsing, and manufactories razed by blasts described as instantaneous. A generator did not simply fracture. It ruptured with explosive intensity, propelling debris through masonry and timber. Investigators frequently discovered no obvious cautionary sign. The aftermath left only shards of iron curled back like parchment. These engines constructed our contemporary world, yet they did so at a significant price. Every parish had tales of a vessel that failed without leniency. Beneath the march of progress lay a reality none wished to face. The energy that propelled industry forward was the same energy that could bring it to total ruin. To comprehend why so many apparatuses failed, one must examine the internal mechanics. Long before the metallurgy ever yielded, vapor tension was not merely a figure on a dial. It was a force that functioned according to axioms most Victorian attendants had never been instructed in. Many stokers originated from backgrounds in joinery, husbandry, or general manual labor. They mastered boilers as they did every craft, by observing the man preceding them. What they lacked was a grounding in thermodynamics, a discipline still being formulated as these engines roared to life. The issue was that steam could transition state more swiftly than human instinct could track. Liquid heated in a restricted volume dilates with remarkable rapidity, and when temperatures surpass particular limits, marginal thermal gains can incite monumental surges in pressure. This was the phenomenon few attendants comprehended. A hearth stoked with excessive enthusiasm, a liquid volume permitted to recede marginally too far, or an atmospheric shift beneath the combustion chamber could transmute a stable vessel into a volatile one within moments. Indicators provided a veneer of reassurance, yet early manometers were notoriously fallible. The Bourdon gauge, pioneered in the mid-19th century, rendered measurements more exacting. Nevertheless, even it was plagued by vibration, deterioration, and calibration discrepancies. In manufactories where particulates and grit permeated the air, delicate apparatuses withered swiftly. Certain dials seized whilst others trailed behind actual states, and many were never scrutinized following their installation. For those in engine rooms, a reading could be comforting, precisely until the instant it became immaterial. Steam engines coupled to these generators also impacted tension in manners that were poorly grasped. Abrupt changes in load, such as machinery engaging or ceasing, precipitated immediate oscillations within the boiler shell. If a substantial piece of hardware halted unexpectedly, the vapor no longer in use recoiled back into the system. This peak could overwhelm the enclosure more rapidly than a stoker could intercede. The correlation between mechanical burden and internal stress was a precarious one, and industrial timetables often compelled equipment to function at the very fringe of that equilibrium. Airflow played its part. Furthermore, hearth drafts were regulated via dampers, though these were frequently rudimentary, sliding iron plates or linkages that staff adjusted by intuition. A flurry of wind entering through a factory portal, or a transition in external meteorological conditions, could modify the ventilation beneath the firebox, intensifying the heat in ways no person anticipated. In wintertime, when apertures remained fastened, the draft could diminish suddenly, then billow again when unbolted. These diurnal fluctuations sufficed to transform routine work into perilous territory. Even the water itself could manifest as a menace. Sediment in feed water produced calcification on boiler surfaces, forming a barrier of insulation that impeded thermal transfer. This forced stokers to overcompensate with fiercer fires. Unaware, the metallurgy beneath the scale was heating irregularly. When the incrustation eventually fractured or delaminated, incandescent metal abruptly encountered cooler liquid, generating violent, instantaneous vapor eruptions. The pressure surge from that event has demolished many a mill. Without warning, pressure climbs were not lingering sagas. They were episodes, fleeting and merciless. Men spoke of perceiving a swift change in the engine's tone, a more acute hiss, or a more profound reverberation. Yet these indicators manifested only seconds prior to catastrophe. By the time the peril was discernible, the physical laws had already assumed command. Long before a vessel detonated, its iron had already commenced the lingering process of capitulation. Every thermal cycle distended the iron plates, and every cooling phase retracted them once more. This incessant dilation and contraction induced stresses that none could observe. In the 1800s, the tenet of metal fatigue was scarcely comprehended, and most fabricators presumed that if a sheet appeared whole, it was robust. The reality was far more intricate. Boilers deteriorated from the core, and the evidence of their enfeeblement could remain concealed until the ultimate disastrous instant. Iron from that epoch fluctuated wildly in excellence. Numerous plates were rolled in mills, lacking modern oversight, yielding metal with irregular density and latent slag impurities. These imperfections were benign under low tension, but lethal under reiterated strain. Over time, microscopic fissures developed along these flaws. They originated as filaments finer than a human hair, yet each thermal cycle broadened them. Eventually, the fracture traversed a plate like a tectonic line, awaiting discharge. By the time any person took note, the impairment was already irrevocable. Riveted assembly introduced its own susceptibilities. Generators were constructed from contoured plates unified by rows of rivets. each aperture bored or punched through the metalwork. These holes established inherent concentrations of stress. As vapor tension throbbed within the vessel, the boundaries of every rivet hole flexed. After years of operation, these minute shifts loosened the rivets and distorted the apertures. A sequence of failing rivets could unseal a boiler seam in moments, discharging steam with volcanic energy. Riveted joints were only as stalwart as their most compromised point, and frequently that frailty lay obscured beneath layers of lagging. Internal oxidation presented another hazard. Liquid utilized in boilers was seldom pure, and contaminants reacted with the iron to generate rust. This corrosion gravitated toward pockets where dross settled, primarily at the vessel's base where circulation was most lethargic. Oxidation corroded the metallurgy from the interior, diminishing it erratically. A sheet might exhibit a reliable thickness in one area, yet be perilously eroded mere inches away. Supervisors of that epoch lacked the apparatus to identify such localized impairment. Many vessels that seemed robust were already compromised, beyond salvation. Longitudinal stays and braces, the internal reinforcements, preventing shell walls from distending, similarly deteriorated with age. These struts endured relentless tension that warped and flexed them, ever so slightly. Should a brace yield or fracture, the surface it reinforced could bow outwards. This distortion intensified stress upon adjacent plating, precipitating a cascade of structural disintegration. Certain detonations were subsequently linked to a solitary stay, which had surpassed its endurance. Without providing any discernible indication, the boiler room milieu hastened this degradation. Elevated moisture, incessant oscillations, and radical thermal fluctuations eroded the framework more swiftly than architects anticipated. The men stationed beside these engines frequently recounted perceiving a subtle clicking or lamentation as the vessel dilated. These reverberations were not admonitions, merely the inherent cadence of metal under duress. Yet they obscured the more profound resonance, the infinitesimal rending that expanded with every operation. Material fatigue was a clandestine adversary. It did not herald its presence with seepages, fissures, or tarnishing. It gathered unobtrusively over years of duty, until the day the generator reached a threshold from which no restitution was possible. When the collapse occurred, it was instantaneous, absolute, and final. The ironwork that had loyally contained vapor for decades surrendered in a heartbeat, leaving only fragments and uncertainties. The boiler house was frequently the most neglected quarter of an entire manufacturing site. It was situated beneath ateliers, behind mills, or below the decks of steam vessels, concealed and far from the scrutiny of executives. To observers, it was merely the furnace that generated steam. To the laborers who functioned within it, the chamber felt like a separate realm, more sweltering, dimmer, and more volatile than any other part of the works. This seclusion fostered a climate in which peril matured silently, protected by masonry that few individuals deigned to visit. Numerous early industrial edifices were not engineered for welfare. Boiler rooms were crammed into residual spaces, cellars or improvised outbuildings, appended long after the primary framework was completed. Their low eaves ensnared the heat. Their brickwork absorbed the tremors. Ventilation was frequently an afterthought, leaving the atmosphere stagnant and saturated with vapor. Manometers clouded, dials perspired, and the scent of humid iron mingled with acrid soot in a manner that made every surface feel animate. Under these circumstances, even mundane duties demanded constant recalibration. The stokers who attended these boilers labored under immense physiological duress. Temperatures habitually surged beyond levels that modern welfare regulations would deem intolerable. Perspiration blurred their vision. Garments adhered to their skin. Coal dust accumulated in the creases of their cuffs. Shoveling fuel into the hearth became a rhythmic struggle, each movement nourishing the engines that energized the entire complex. With every spadeful boot, the stoker was required to interpret the character of the blaze, the draft within the chimney, and the subtle transitions in the boiler's resonance. These were proficiencies mastered via practice, not formal tuition. As the engine room was shielded from the public eye, circumstances frequently declined below tolerable benchmarks. Seepages were mended with improvised remedies. Valves were scoured only when they became problematic. lagging detached from the conduit and was never reinstated. Executives concentrated on output deadlines, seldom descending the stairs to inspect the condition of the plant. Their grasp of the room's requirements was derivative, conveyed through laborers, who prioritized the continuous running of the works over requesting maintenance. This chasm between management and reality widened annually. Illumination was substandard in many boiler houses. Lanterns threw wavering circles upon soot-begrimed walls, rendering it simple to overlook indications of distress. Dampers and control linkages oxidized in the shadows. Rust developed unnoticed upon mountings and flanges. Vapor escaped from joints and vanished into the muggy air before it could be traced to its origin. In this murky environment, men depended on tactile sense and sound as much as sight. A detached bolt or quivering pipe might be identified by touch. Long before it became visible, clamor added a further dimension of hardship. The relentless roar of the furnace, the reverberation of engines overhead, and the rhythmic throb of the pumps established a setting where subtle admonitions were easily forfeited. A shifting plate or a straining internal stay resonated no differently from the habitual groans of machinery. Even should a laborer sense an abnormality, conveying that anxiety up the hierarchy was not always straightforward. Stokers frequently bore the reputation of being excessively wary or inclined to fret. Their cautions were not always regarded with gravity. This physical and cultural seclusion rendered the boiler house a blind spot within the industry. It was a domain where engines aged without oversight, where hazards accumulated unobserved, and where those most intimate with the hardware possessed the least authority. When a breakdown eventually occurred, it was not merely a mechanical incident. It was the culmination of years spent in the shadows, obscured from sight and neglected by the mind. The instant a vessel fails is not a lingering disintegration, but a violent confrontation between tension and architecture. Within every shell, vapor is perpetually seeking liberation. As the thermal level ascends, molecules strike the boundaries with escalating ferocity, scrutinizing every seam and every sheet. On most days, the boiler prevails. But when the internal pressure finally surpasses the robustness of a single flaw, the consequence is instantaneous. There is no pause, only the abrupt victory of tension over iron. That vulnerability could be situated anywhere. At times it was a plate thinned by clandestine oxidation. Elsewhere it was a row of rivets strained to their breaking point. After decades of duress, even a minute blemish no wider than the rim of a farthing could seal the destiny of the entire framework. Once the pressure identified this susceptible point, the fissure propagated with immense velocity. Metal does not rend gradually under a vapor load. It ruptures in a solitary, ruinous movement. The primary indication of failure noted by survivors was often acoustic, not a bellow, but a piercing crack, like a cannon discharged within a confined space. This was the metallurgy capitulating. The force within expelled the weakened iron outwards, establishing an aperture that dilated immediately. Steam surged through the breach with brutal acceleration, discharging at speeds exceeding hundreds of miles per hour. In that instant, the vessel ceased to be a tool and became a weapon. The rupture did not remain isolated. As vapor escaped, the pressure in the intact portions of the boiler shifted radically. This disequilibrium exerted immense stress on adjacent sheets and seams. A failure in one section frequently ignited secondary collapses. Moments later, examiners inspecting the wreckage of detonations habitually found the generator rent into numerous sections, each shard propelled in a disparate trajectory by the abrupt discharge of latent energy. Within factories, the expanding vapor stunned whole chambers. Laborers recounted being cast off their feet, blinded by incandescent mist and deafened by the percussion. On steam vessels, the impact could shred through the decks and propel machinery into the heavens. Timber beams fractured, brickwork buckled outwards. Even heavy apparatuses anchored to the flooring were occasionally dislodged and cast across the hall. The ferocity was not merely ruinous, it was transformative, converting solid matter into debris, strewn across astonishing distances. The physics governing this force is found in the quantity of energy held within superheated liquid. When water exists under tension at elevated temperatures, nurtures far greater energy than boiling water at atmospheric levels. Once pressure is forfeited, the superheated liquid flashes into steam, expanding instantly with volcanic intensity. This flash, known to contemporary engineers as a rapid phase transition, was poorly understood during the Victorian steam age. To the individuals who witnessed it, it appeared as though fire was erupting from the water. The aftermath invariably recounted a consistent tale. Iron plates were curled backwards, rivets were sheared precisely, and shards of the vessel lay embedded in masonry or rooftops. From these markers, investigators mastered the art of tracing the origin, the site where pressure identified its opportunity. Every detonation unveiled a moment in which the internal force overwhelmed the final boundary. The remainder unfolded in fractions of a second. What rendered these moments so lethal was not just the power of vapor, but the velocity at which the events transpired. A generator could appear stable right up to the instant of failure. There was no countdown, no visible or audible accumulation of peril. When the weakest point finally capitulated, the entire narrative concluded almost immediately. The most unsettling aspect of boiler failures is how often cautionary signs were present long before the terminal rupture. These clues were subtle, inconsistent, and easily dismissed within the daily clamor of industrial life. During the 1800s and the early 20th century, generators did not possess diagnostic systems, monitoring sensors, or automated alarms. They relied entirely upon human faculties, and human perception was not evolved to interpret the dynamics of steam. Consequently, peril frequently resided in plain view, unidentified until it was too late. One of the most primitive indicators of distress was irregular heating. When a vessel heated more precipitously on one side than the other, the iron sheets expanded at disparate rates. This established internal stress configurations that could ultimately culminate in failure. Yet stokers seldom observed the boiler's exterior altering its profile. Instead, they might perceive a faint, rhythmic cadence or an anomalous tremor in the flooring. These signals were so negligible, so easily disregarded, that they rarely provoked apprehension. Industrial environments were saturated with cacophony. One additional noise was merely part of the ambience. Liquid-level oscillations provided another indication. Boiler sight glasses were slender tubes, intended to display the elevation of the water within. If the liquid fluctuated or receded unexpectedly, it could signify the formation of a vapor pocket, or circulation impediments deep inside the vessel. However, sight glasses were susceptible to fouling. Minerals accumulated upon the glass, rendering the readings opaque. Certain operators struck the tubes to dislodge the sediment, oblivious that the erratic motion of the water portended something far more grave. A momentary subsidence in the column might be the solitary warning. Before the vessel endured a sudden and hazardous surge in internal pressure, safety valves, engineered to open when tension surpassed safe thresholds, were intended to serve as the boiler's ultimate safeguard. In truth, they manifested their own subtle admonitions. A valve that rose momentarily and reseated with a sharp hiss was informing attendants that pressure was approaching the limits of safe operation. The workers, habituated to antiquated machinery, became accustomed to these sounds and regarded them as routine. When a valve activated too frequently, some even tightened the mechanism to suppress the noise, unwittingly disabling the one component capable of averting a catastrophic event. Another disregarded sign originated from the furnace itself. In coal-fired generators, the hue and motion of the blaze disclosed conditions within the combustion chamber. A fire glowing too intensely or surging erratically signified draft complications or a disequilibrium in heat distribution. Yet many stokers were never instructed to interpret these details. Their priority was the continuous running of the machinery, not the analysis of combustion behavior. A flame that flickered more violently than customary might indicate a boiler plate was warping under extreme duress, but to the men at the hearth door, it was merely another instance in a protracted shift. Even seepages, perhaps the most conspicuous warning, did not always incite immediate concern. Vapor escaping from joints or couplings was so prevalent that many laborers accepted it as a facet of daily operation. A minor jet of steam might hiss from a flange for months without incident. Only when the leak intensified or the sound altered did anyone contemplate deactivating the system. By that stage, the internal damage was often well advanced. The danger lay not in the absence of signs, but in the fact they were subtle, inconsistent, and easily misconstrued. In the era of steam, a boiler provided intimations of its state, but it spoke in a dialect most men were not tutored to comprehend. When those intimations went unobserved, the trajectory toward failure was already established. Relief valves were intended to stand between a functional vessel and a ruinous collapse, yet they were among the most misunderstood apparatuses. In early steam power systems, these valves were uncomplicated in principle, a calibrated mechanism designed to lift when tension exceeded a safe boundary. But during the 19th and early 20th centuries, the reliability of safety valves was contingent upon craftsmanship, maintenance, and environmental factors that were far from uniform. For many boilers, the valve was not merely a precaution, it was the final line of defense when all else had faltered. The earliest relief valves were rudimentary devices, little more than weighted lever arms positioned over an aperture. Their operation depended upon the precise equilibrium between the pressure of the vapor below and the gravitational or spring force applied from above. As long as that balance was maintained, the valve remained sealed. When vapor tension surpassed the prescribed level, it compelled the valve upwards and vented the excess pressure into the atmosphere. In theory, this simple mechanism should have averted innumerable accidents. In practice, it was vulnerable to almost every hazard present in an engine room. Dust and soot were persistent enemies. Coal-fired furnaces produced fine particulates that settled upon every surface, including the sensitive moving components of the safety valves. When sufficient residue accumulated beneath a valve seat, it prevented the valve from sealing entirely. Attendants occasionally observed a faint plume of vapor escaping from the mechanism and endeavored to suppress it by tightening the fitting. This makeshift solution engendered a new peril. By intensifying the tension upon the valve, they unwittingly elevated the pressure threshold far beyond safe parameters. A valve intended to activate at one level might now refuse to lift until the vessel entered a hazardous state. Corrosion afflicted valves just as it did the boiler plates. Atmospheric moisture and impurities in the steam bred rust on hinges, springs, and contact surfaces. A corroded spring forfeited its elasticity. A rusted hinge resisted movement. In frigid weather, valves could even freeze in position. Many failures were subsequently traced to valves that had not opened in years, not because the boiler never approached its capacity, but because the mechanism had silently seized. Operators often discovered the fault only after a detonation, rendered the damage impossible to ignore. Tampering introduced a further layer of risk. Some plant proprietors regarded relief valves as a nuisance. When they activated, they discharged valuable steam, diminishing the available energy for the works. In a competitive industrial milieu, output was the sole priority. There were recorded instances of valves being pinned, weighted, or shackled to prevent their opening. Inspectors occasionally identified makeshift modifications, such as metal straps or bolts, appended by laborers under duress to maintain production. These alterations transfigured the valve from a safety apparatus into a focal point of failure. Calibration was another neglected challenge. A safety valve required setting with utmost precision, yet few facilities possessed the instruments or expertise to conduct accurate adjustments. Valves were occasionally calibrated by conjecture or based upon previous settings without verification. Springs weakened with age, threads eroded. The intended pressure tolerance drifted over time. A valve that once provided dependable protection could become perilously erratic. After years of neglect, when a relief valve finally did open correctly, it was frequently described as a violent, startling event. Steam was blasted into the air with a roar that reverberated through the edifice. Laborers felt the tremor through the floorboards. The sudden discharge was harrowing, but it signified the system had a chance to stabilize. Yet should the valve fail to lift at the critical juncture, the boiler was left without any pressure outlet. In that instant, the entire shell became a sealed vessel of escalating force. Safety valves were the final barrier between controlled power and unbridled destruction. When they functioned, disaster could be averted. When they failed, nothing else remained to impede it. When a vessel failed, the magnitude of ruin often defied belief. Boilers were formidable machines, forged from thick iron and weighing several tons, yet a detonation could launch them through masonry walls or send them soaring through the air like artillery shells. These events were not localized bursts, but sweeping blasts that transfigured entire edifices in a matter of seconds. Factories, mills, locomotives, and riverboats, all left behind. Grim chronicles of what a sudden discharge of vapor energy could achieve. Investigators scrutinizing the remains of demolished buildings found patterns that became disturbingly familiar. Walls were forced outwards, floors buckled, and beams were uplifted as if struck from below. This upward force disclosed a vital detail regarding boiler detonations. When a ruptured vessel released its pressure downwards, the jet of escaping steam functioned like a rocket engine, propelling the remaining mass upwards with incredible velocity. Certain boilers were discovered hundreds of yards from their original site, embedded in fields or resting upon adjacent rooftops. Their flight trajectory illustrated the energy. Unleashed in mere fractions of a second, the shockwave generated by escaping vapor traveled swifter than human reaction. It dilated outwards through workshops, crowded with machinery and laborers. Tools, drive belts, and gears became projectiles. Windows imploded, casting glass across rooms in glittering arcs. Even robust timber beams splintered under the expanding force. Survivors often described the sensation not as heat, but as a violent displacement of the atmosphere, akin to being struck by a sudden gale, powerful enough to lift them from their feet. Steamboat explosions were exceptionally devastating. Boilers mounted upon decks or between cabins possessed no solid masonry to contain the blast. When one failed, the superstructure of the vessel provided negligible resistance. The force rent through wooden planks, fractured masts, and cast passengers into the depths. Certain detonations ignited conflagrations that consumed the vessel within minutes. The Mississippi River became infamous for these tragedies, with ships such as the Sultana and the Pennsylvania leaving behind scenes of carnage that unfolded without intimation. In factories, the devastation often extended far beyond the boiler house. Explosions could ignite coal dust, timber shavings, or oil residues, transforming the initial blast into a chain reaction of minor fires and secondary detonations. In textile mills, lint suspended in the air ignited in brilliant flashes. In sawmills, resin-soaked timber burned fiercely, once exposed to intense thermal energy. The primary failure of the boiler served only as the prelude to a much grander catastrophe. The shockwave fractured adjacent machinery in erratic ways. Cast iron gears fissured, drive shafts buckled or snapped. Overhead line shafts, rotating at high velocity, were wrenched from their bearings and lashed across workrooms like metallic flails. These secondary failures were responsible for many casualties, as laborers struck by airborne equipment often had no inkling where the danger had originated. Buildings struck by boiler detonations seldom survived intact. Roofs were hoisted from their frameworks. Brickwork fractured along mortar lines. Doors were torn from hinges and discovered far from their original stations. Insurance investigators scrutinizing these sites concluded that no material available at the time could reliably withstand the force of a boiler failure. Even reinforced walls crumbled when the internal tension of superheated vapor was unleashed. The ferocity of these explosions left communities appalled. Periodicals published illustrations of mangled structures and fragments of boilers lying amongst the debris. Each incident served as a stark reminder that steam, for all its utility, carried a destructive potential that rivaled gunpowder. The men who labored in these settings recognized the risks, but witnessing the aftermath firsthand was something altogether different. It revealed the true magnitude of the energy they coexisted with daily. For decades, boiler explosions were regarded as unfortunate accidents, rather than preventable failures. Factories were rebuilt, riverboats were repaired, and railways replaced locomotives, without fundamentally altering the conditions that permitted these disasters to occur. The notion that government oversight might be necessary was contentious. In an age that prized industrial liberty above all else, proprietors feared interference, engineers mistrusted external authority, and politicians hesitated to obstruct the engines of national prosperity. By the time meaningful regulation began to take form, the death toll had already reached staggering proportions. The first significant impetus for oversight arrived in the mid-19th century, driven not by industry, but by public indignation. Newspapers habitually printed harrowing accounts of steamboat explosions, mill disasters, and shattered workshops. The imagery of buckled boilers and collapsed edifices appeared, alongside rolls of the deceased, many of them laborers whose names were known in their parishes. Public sentiment began to shift. People questioned how such formidable machines could be left without standardized inspection or enforceable protocols. England took early measures, establishing inspection committees and issuing formal advice. But compliance was often discretionary. Many owners resisted, citing expenditure, inconvenience, or confidence in their own methods. In the United States, the situation was even more disparate. Individual states attempted to enact laws requiring inspections, yet enforcement remained inconsistent. Without federal standards, a boiler deemed hazardous in one state could be relocated and operated freely in another first. This patchwork of regulations permitted neglect to endure. The turning point followed a sequence of high-profile disasters that captured the national attention. One of the most influential was the detonation aboard the steamboat Sultana in 1651, which claimed the lives of more than 1,000 people, rendering it one of the deadliest maritime catastrophes in American history. Inquiries revealed corroded boilers, substandard repairs, and disregarded warning signs. The magnitude of the tragedy made it impossible to ignore the necessity for systemic reform. Outrage compelled legislators to confront the fact that an unregulated steam industry posed a menace far beyond the factory gates. In response, governments began establishing dedicated regulatory authorities. The United States instituted more formal oversight for steamboat inspections, and by the late 19th century, organizations such as the American Society of Mechanical Engineers emerged to formulate technical standards for boiler engineering and upkeep. These nascent codes introduced uniform manufacturing specifications, defined safety margins, and advocated for routine inspection protocols. They signified a transition from reliance on operator discretion to a framework established upon engineering principles. Nonetheless, the adoption of these criteria was not instantaneous. Many works operated antiquated vessels long after the new regulations were enacted. Inspectors encountered opposition from proprietors, who perceived safety mandates as an unwarranted encumbrance. Certain enterprises contended the downtime for examinations would jeopardize productivity. Others simply lacked the capital to replace degraded equipment. The friction between safety and profit retarded the impact of reform, permitting hazardous conditions to endure well into the 20th century. Gradually, however, the evidence became impossible to disregard. Statistics demonstrated that regions with enforced oversight experienced precipitous declines in boiler-related casualties. Engineers embraced the new codes, recognizing that standardized design and testing enhanced reliability. Underwriters began stipulating compliance as a prerequisite for insurance cover, establishing financial incentives for safety. Incrementally, the culture surrounding steam pressure evolved. What had once been viewed as an inevitable risk became acknowledged as a preventable hazard. Yet even with these advancements, the question persisted. Had regulation arrived decades too late? For the families who lost kin in the early detonations, no amount of reform could rectify the past. Entire communities bore the scars of disasters that might have been averted. The belated arrival of oversight was a reminder that progress often pursues tragedy, and that the price of industrial expansion had already been paid by those who labored closest to the furnace. Even after regulations reshaped the industry, the fundamental peril within every vessel remained unchanged. Vapor did not alter the physics of pressure. Heat and phase transition continued to operate with the same remorseless logic that had sundered riverboats and mills a century prior. Modern engineering reinforced vessels, refined controls, and added tiers of protection. Yet the elemental force confined within those steel shells carried the same capacity for devastation. It remained a power that demanded deference from any who labored near it. By the early 20th century, modern boilers utilized high-tensile steels and welded seams, which eliminated many of the vulnerabilities inherent in riveted designs. Superior metallurgy reduced internal impurities, and more fastidious manufacturing techniques guaranteed uniform plate thickness. Yet these refinements did not eradicate the risks. Boilers now operated at higher pressures and temperatures than their predecessors. The energy they contained was more potent, and the repercussions of a failure could be equally severe. With advancement came novel forms of vulnerability, some obscured within the complexity of modern systems. Automated controls assisted in stabilizing pressure, but they also fostered a reliance on technology that could veil subtle mechanical issues. A malfunctioning sensor or a sticking valve could permit conditions to drift into unsafe territory without immediate detection. When early boilers failed, the indicators were physical, rooted in the behavior of iron and flame. Modern systems introduced electronic components that aged in disparate ways, occasionally failing silently before their mechanical counterparts exhibited any strain. Water chemistry remained a critical factor. Modern boilers required meticulously treated feedwater to prevent corrosion, scaling, and the accumulation of deposits that could compromise heat transfer. Even with sophisticated purification systems, minor deviations in chemical balance could initiate insidious forms of deterioration. A microscopic flaw in a weld, a thin layer of scale upon a tube, or a pocket of oxygen trapped within the circuit could generate weak points that dilated over time. Vulnerabilities were no longer as overt as rusted plates or failing rivets, but they were present nonetheless. Inspections improved dramatically, and modern technicians relied upon ultrasonic testing, radiography, and pressure assessments to detect internal flaws. These tools allowed engineers to perceive what earlier generations could not. Even so, no inspection method was infallible. Certain defects remained invisible until they expanded sufficiently to threaten the integrity of the vessel. The same unpredictability that haunted 19th-century operators still lingered at the periphery of modern practice. Engineers recognized that a boiler, regardless of how meticulously maintained, was perpetually being stressed by the forces it contained. There were constant reminders of this reality, dispersed throughout industrial history. Mid-20th century, power stations suffered tube ruptures that discharged steam jets, capable of severing through solid metal. Marine engines experienced failures that inundated engine rooms with scalding vapor. Even within stringently regulated environments, accidents transpired when a solitary component failed in a singular, catastrophic manner. At the most inopportune moment, these incidents served as a sobering admonition that the equilibrium within a boiler was perpetually delicate and always shifting. Boilers remain indispensable to power generation, manufacturing, and global transport. Their engineering is more robust, the oversight more rigorous, and their materials far more sophisticated. Yet the principle that precipitated every explosion in the age of steam still pertains. Whenever water is confined, heated, and pressurized, the potential for a sudden discharge exists. Modern systems have mitigated that risk, but they have not abolished it. Behind every gauge and control console resides the same force that once sundered entire edifices. Steam bequeathed the world immense progress, but it never abdicated its capacity for destruction. The physics that dictated the earliest tragedies still waits quietly inside every modern vessel, unaltered and patient, commanding deference from anyone who stands within reach of its power.